Welcome back, everyone. So, today we are diving into an explainer that I am incredibly excited about. I'll be your tutor as we demystify differentiation, specifically tackling the real meat of pure mathematics 3. We're going to take these big, sometimes intimidating advanced concepts and just break them right down into super simple visual steps. You're going to walk away from this with a rock-solid understanding, I promise. Let's get right into it.
But hey, before we start throwing a bunch of equations and formulas at the wall, we need to address the elephant in the room. Why do we even study differentiation anyway? Let's actually ground this learning journey in reality for a second.
Because look, it really isn't just a bunch of arbitrary algebra. Differentiation is literally the mathematical foundation for calculations in quantum mechanics and field theories in physics. Basically, when we differentiate, we're calculating the exact rate at which things change. And since our physical universe is constantly changing, the tools we're reviewing today, they're the exact same tools physicists use to decode the fundamental nature of reality. No joke. You aren't just doing math here, you are speaking the literal language of the universe.
So to get us fluent in that language, here's our roadmap for today. Number 1, finding stationary points. 2, exponentials and logarithms. 3, tackling trigonometric functions. 4, product and quotient rules. And finally, number 5, implicit and parametric differentiation.
All right, let's kick things off with section 1, finding the stationary points, and really grounding our math.
Okay, so imagine you're out hiking through a huge mountain range. You're trekking up steep hills, dipping down into deep valleys. A stationary point is simply that split second at the very top of a peak or the absolute bottom of a valley, where the ground is perfectly flat before you start going down or up again. Right at that point, the gradient is exactly 0, which in calculus speak means the first derivative, f prime of x equals 0. But here's the catch. How do you know if you're standing on a hilltop or standing in a valley? Well, that's where the second derivative, f double prime of x, swoops in to save the day. It gives us a brilliant rule of thumb. If the second derivative is greater than 0, the point's nature is a minimum. You're in a valley. But if that second derivative is less than 0, boom, it's a maximum. You're on a hilltop. So first derivative finds the flat spot, second derivative tells you its shape. Pretty simple, right?
Moving right along to section 2, exponentials and logarithms. It's time to level up. Now, I want you to notice the sheer, beautiful simplicity of these highly reliable patterns. Take a look at the exponential derivative over there. The derivative with respect to x of e to the power of x is literally just e to the power of x. It's its own derivative. It's a function where its rate of growth perfectly matches its current value. How cool is that? Then if we look at the logarithmic derivative, the derivative of the natural log of x, ln x, transforms into this incredibly clean, simple fraction, 1 over x. As a tutor, I absolutely love teaching these because once you spot the pattern, you realize you don't have to overthink it at all. You just apply the rule and keep moving.
Next up, section 3, tackling trigonometric functions and seeing the cycles.
I know, trigonometry can seem totally overwhelming, but just think of this as your handy visual glossary. Just like the exponentials we looked at, trig functions follow this awesome cyclical nature. When y equals sine x, its derivative is simply cosine x. And when y equals cosine x, the derivative flips to negative sine x. They just do this little dance back and forth. For tangent x, the derivative becomes secant squared x. And for the inverse tangent, tan to the negative 1 of x, it becomes 1 over the quantity 1 plus x squared. The crucial takeaway here, please do not try to reinvent the wheel. You just need to keep this toolkit in your back pocket, recognize the pattern, and definitely don't panic.
Okay, section 4. Product and quotient rules. Let's start combining functions.
So this is where things get really fun. We're going to look at what happens when our base functions actually start interacting. Sometimes a function is essentially two totally separate functions multiplying each other. Like, think of x squared multiplied by sine x. We can't just differentiate them normally. We need the product rule. And I've broken this down into 3 super manageable bite-sized steps for you. Step 1, identify your 2 functions. Just call the first one u and the second one v. Step 2, go to the side of your paper and differentiate u and v completely separately. Step 3, combine them using a little crisscross pattern. You multiply u by the derivative of v and then add v multiplied by the derivative of u. And there you have it. You've just navigated a complex product using nothing but basic algebra. But wait, what if those functions are dividing each other instead of multiplying? Well, then we use the quotient rule. Now, the mathematical formula for this can look like an absolute nightmare, just a terrifying alphabet soup of u's, v's, and fractions. So let's skip the headache. Instead, I want you to read this catchy word-based mnemonic straight from the source text. Denominator times derivative of numerator minus numerator times derivative of denominator, all divided by the denominator squared. See? It kind of has a rhythm to it. If you just memorize this little word pattern, applying the quotient rule goes from a test of complex memorization to a really simple fill-in-the-blank exercise.
And finally, Section 5, Implicit and Parametric Differentiation. We've made it to the final level.
You guys are now fully equipped with the calculus toolkit to handle some real complexity. So let's finish this explainer strong. Up until right now, every single function we've looked at had y sitting there nice and neat all by itself on the left side of the equal sign. But as we know, the universe is rarely that neat. An implicit function is what happens when y is not the subject. It gets all tangled up inside the equation with x. Like in the example, x cubed plus y cubed equals 5x. When you run into this, don't even waste your time trying to untangle it to isolate y. We just differentiate both sides of the equation exactly as they are, relying on the chain rule and product rule we just went over. Basically, we just embrace the tangle.
Okay, now let's look at one more way these variables can interact. Sometimes x and y aren't connected to each other directly at all. Nope. Instead, they are both being controlled by a hidden third variable, which we call a parameter. This is usually represented by the letter t for time, or maybe the Greek letter theta for an angle. Think of the parameter as this invisible string pulling from behind the scenes. As t changes, it pulls on x and it pulls on y at the exact same time, tracing out a path.
To really make this concrete, let's check out this table generated from parametric equations. Right across the top row, we have our hidden parameter, t, steadily moving from 0 all the way up to 2 pi. By plugging these specific values of t into our parametric equations, it directly generates the x-coordinates and the y-coordinates that you see in the rows right below it. Do you see how t is completely dictating where both x and y need to be at any given millisecond? So if we take these x and y pairs and plot them on a graph, we get something absolutely stunning. Just look at this. This is a Lissajous curve. Now, if you tried to draw this using standard explicit math, it would be an absolute nightmare. But through the simple step-by-step plotting of parametric equations that we just saw in the table, it emerges naturally and beautifully. It's the perfect illustration of how breaking down math into these fundamental rules allows us to graph and truly understand the highly complex looping shapes of our world. And wow, that brings us to the end of our journey today. We've conquered finding stationary points on mountain-like curves, we've navigated exponentials and cyclical trigonometry, and we've combined functions using rules that are now, hopefully, clear, logical steps. You've even learned how to wrangle hidden parameters and implicit tangles. You haven't just memorized a bunch of dry formulas today. You've literally acquired the exact calculus toolkit used to explain the intricate mechanics of the universe. So, I'll leave you with this. Now that you have these incredibly powerful tools in your hands, what complex patterns of our universe will you decode next? Thank you so much for learning with me today. Keep practicing, stay curious, and I will see you in the next explainer.